All right, here we go. Welcome to PLC3 Week 11, Servo Motors, and you are watching this either out of the PowerPoint we click on the video, or some people have subscribed to the channel. Nice, and so you automatically get it, and you got to figure out some way to monetize that. I'll keep you posted on that. Anyways, taking attendance, I'm take a look at see what's going on. Everybody's been doing pretty good for labs. No quiz this week, so I guess trying to get caught up to where we would take the state machine and phase manager quiz probably next week. All right. New handouts for you and stuff posted on D2L. A little bit of homework on servo motors, the lab on servo motors, some D2L reading on servo motors. And then this week, we have the servo motor control board that I'm still kind of putting together, or maybe I'm going to have you put together just to dig into literature a little bit and see what's involved in hooking up that Kinetics 5500 board. But before we do that, we'll take a look at our week 10 review. It was phase manager, and once again that was still a bit of a catch-up lab, and we did do well getting through this, and everybody's going to be through the last bit of this phase manager pretty quickly, I think. And so just to reiterate, phase manager is a built-in function of the control software. In this case, RS Logic or Studio 5000 is what it is. It's not in the older versions. But that there might be larger platforms that would have this kind of phase manager feel to them, and it is utilized with HMI to control the process. Everybody thought it was kind of cool the way that it moved through it, and I just wanted to introduce it to give you a feel for how it works, and some advanced scheduling. A lot of PLCs today, that's what it is. Like, how do you schedule all this stuff? And when something breaks on a big process, how do you even find out what's going on or what should be going on? So now I'm going to go through some of these slides that are similar to what we did last week, but now that you've done it, maybe it just reiterate a little bit and hit home, and then we'll take the quiz on it, not this week, but next week. So our quote equipment phase consisted of a blinking light. Not much. You would have really big equipment phases going on if you reach the point where you were using a phase manager. Scheduling be accomplished in a variety of different levels, whether the phase manager was running the overall process, and within that process, those equipment phases, you would have state machines running it and scheduling all your subroutines, and things like that. It could get very complicated. I'm not sure you'd want to use the phase manager on something that's simple. ISA 88 talks about all this. There's a lot of documentation about the theory behind state and phase manager, related to your equipment models, how the equipment would be standardized into procedural models of how you would standardize all this. So someday, if you're a heavy-hitting controls engineer, or you're working for a company that's got big processes, maybe you'll become an expert on this, but in PLC 3, not today. So these are just about 4 slides from the last PowerPoint, like I said, to talk about the things that we covered. And so once again, our equipment phase was pretty simple, and basically it just the main thing is this defines the link to the physical equipment. Okay, and we can pass variables in and out of these phases, and it's going to follow some type of a state machine or state model. Okay, it says contributes to a complete recipe. A full batch recipe is made up of a sequence of equipment phases. So a full batch recipe would be these equipment phases, like you might be adding components, you might be mixing components, you might be drying components, whatever they would be executed in order to produce the final product. Our equipment phase was just a blinking light. Hopefully that makes sense of how something bigger might work. And so when we went through this, it was kind of cool. I like the way it runs. It did have, I was seeing some of these with, we put a 5-second delay for resetting and shutting down and all this kind of stuff. It was cool. It kind of felt like a little a machine with a lot of equipment phases, even though it was very small, just a blinking light. But you have these pre-state and these active states that you went through, like running, holding, restarting, only one active at a time. You were able to access the states on the through the PCMD and PSC and the HMI on these tags that automatically get generated. Okay, so that was some of the functionality that you worked with on this equipment phase. And so once again, just the best practice, you want to isolate your phase logic. You want to keep it in this respective phase. You want to manage your state transitions, just so that whether you're using a state manager or phase manager, that you are when you transition into the different state, that that the other state is finished or holding or is not doing something that it should have been. And it's used for complexity. Ours is a blinking light, pretty simple, I know it. But if you get something really complex, is what you're going to have in your scheduling, and everything will get super fancy, and you'll probably have best practice that you like to do. And then so you'll have AOIs to do this. You'll use your own AOIs probably that will come in and do scheduling within scheduling and set all your states and stuff like that, right? These were some of our common states that you used. And I'm not going to break them all down, but when you were pausing or paused or holding or held, that's when we put the 5 seconds, and it was cool. It did kind of give that feel of a big process, even though we were blinking the light. And then I like this, that you had to print this off. I like the people that printed this off big and made notes on it, because you do have to follow the arrows depending on what you're trying to do here. And you're like, wait a minute, did I have to do this? Oh, wait a minute, I got to stop it. Then I got to reset it. Then I got to, start it, or I got to restart, and I don't have to reset, and just follow the little bit of flow right here of your phase manager. Okay. Another thing that I want to talk about real quick that we didn't do, and that was the ability for the HMI to really play a bigger part in this. I like the way that you use the HMI. It was cool, getting some functionality between the phase manager and the HMI, and then showing what was going on. But really, in Factory Talk View, there's a little icon in the lower left, just above your Factory Talk View, or your communication setup. Okay, just right above the communication setup. We always run the communication setup, but right below that, you'll see Recipe Plus, and that you can click that, and it will launch into Recipe Plus, where you can build your recipes, and there's also libraries in there. You can go right to the libraries and pull up tons of different recipes that give you the kind of feel, and you can modify from there. In this, you can set up your recipe management right in the HMI, and that's where you define, save, edit, manage different sets of values, that your ingredients and parameters that can be downloaded to the PLC or other process device. So all these recipes get created in the HMI, in the MER, okay, and then they get sent, and they kind of program the PLC. We'll talk about it a little bit, but that gives the operator the ability to kind of program the PLC without really programming it. It just simplifies the operator interface. The recipes are just data sets where you list the ingredients, parameters, tags, values, names of what's being manufactured, and then some other things are mobile access. You can take a look at this stuff via web browser or something like that if you're not on site. And so that is the next step that we're not going to get into, would be to use Recipe Plus on Factory Talk View. I don't think we're going to get into it. We could possibly do something like that on the capstone if you really want to dig into it. So now our model is getting to look pretty cool here, our master-slave model, where the PLC does remain the master. Everything's kind of coming through the controller here. But I've got my arrows, I got big arrows, and I got little arrows here. So you got the HMI, and it's got a big arrow going to the PLC. Because that HMI, especially if you're using like your Recipe Plus, that's going to push your recipes into the PLC. So that's kind of like almost like I said, like the operator programming the PLC, but really they only have a limited values that they can enter, input, IO fields, process variables, that kind of thing. And I got this little arrow here. So yeah, the PLC does send some information back to the HMI, in probably just so the operator can monitor, what is going on. But that HMI can you know, that big arrow, get a push to the PLC. Now the PLC is good at multitasking. We talked about that. You can run multiple programs. It goes through the scan, and it will you'll schedule your routine, schedule your programs. You can do your phase and your state machines to run everything in order, but it can be running multiple routines at once or multiple programs. It does have to scan and run, you know, one at a time, but it does it very fast. All right. So I'm going to say that's multitasking. And then I've got the arrows here up and down because the field devices, you know, the PLC is pushing out signals and it's receiving signals from the field devices, your sensors, actuators, drives, whatever you got connected to the PLC. Okay, and it's using that information to make decisions, and it's making decisions and pushing out to the field devices. There's some monitoring, stuff like that. Okay, and we've been doing a lot of that. That's mostly what we've been doing. And then you got the next PLC, and I've got the big arrow here because it really is controlling this robot. It is pushing out information to the robot, calling different programs, telling it to continue on your program. And realize that a robot is not good at multitasking. For example, it might go to position 1, then it might call subroutine 1. And then all of subroutine 1 has to run all the way through, and it must end the subroutine, and then it would come back and go to position 2. And the next line, if input 1, it was jump to a label, wherever that label would be. It can't jump around in this program and run multiple things at once. It just does one line at a time. And if you call a subroutine, it has to complete that subroutine and then come back. Now, you can call subroutine 1 or call subroutine 2 or call subroutine 3, but it still needs to call that subroutine. Run every line in order in that sub, jump back, and then figure out if it's calling the next sub or if it's jumping over that line to the next one. So not good at multitasking. But the robot can send information back to the PLC. It's going to send information back like, hey, I'm done with this process. You know, what do you want me to do now? And the PLC will tell it at the same time while it's telling the field devices what to do and pushing a little bit of information to the HMI saying, hey, by the way, the robot's waiting or running. But, you know, the HMI, the information that it's sending there is critical, you know, like the information that it's sending to the field devices or the robot. So hopefully that makes sense. And we'll do a little bit of robot programming in the class to have the PLC control the robot. And so the capstone, we can tie all this in together just to see how it all works. But that's what we didn't really get into as Recipe Plus for the HMI, but I think you're getting the idea there. Okay, so now we're going to work on talk about motor control because we're going to work on servo motor. So a lot of this is just kind of I don't know, it's a little bit of a review just to talk about, you know, where we've been and just be sure you're fully up to speed. And we're going to talk about start-stop motor memory, PLC control of a motor circuit. This is kind of how we evolved through your classes here. Speed control of electric motor, VF control of electric motor. We've done that. Now we want to do to stepper motor control and servo motor control is what we want to talk about. So, you know, just to start our review, we want to just review AC motors. Now what I've got here is I've got 3-phase AC motor windings shown. You know, if it was single phase, originally I teach this with single phase, you know, so it might just be the red and the red showing a single phase for you to get the idea that, you know, if one of these is plus and the other one is minus, and then it's showing the road here, you know, north, south, plus, minus. So you get the idea that this has to flip around and then flip around again. It goes plus to minus, minus to plus. It has to make a complete rotation, you know, every 60, you know, 60 times per second. But I'm showing 3-phase because, you know, we learned that 3-phase, when you got 3 windings, you get a lot higher performance out of this motor because you're showing your 3-phase electricity right here instead of your single phase. You got these being 120 degrees. So every 120 degrees, you're getting a little bit of work out of these things. So that motor is going to be, you know, like I said, you get a lot more power out of it. Your efficiency, you know, all these things, a 3-phase compared to a single phase. But we've already been over this in 131, and I'm sure that this makes sense. So this right here is just showing motors, once again, 3-phase motors. This is 1 red, 2 red, 3 red, 4 red. So that's my 4-pole. And this is 1, 2, 3, 4, 5. That's my 6-pole right there. But there's 3 phases, so everything's timed by 3. So we're talking about 60 cycles per second electricity, but there's 3 phases. But if we just think about single phase, 3,600 seconds a minute. In one complete cycle, 60 cycles per second. So in a second, it goes from positive to negative, back to zero. So 0 goes to positive to negative, back to 0. And so you get a push, I guess, or a positive in a pull, and then you get it goes negative, and you get a push and a pull on the downside of this every rotation. So you get 2 push, and at the bottom of the cycle, it switches from a pull to a push and a push to a pull. So one complete cycle being plus or minus. So your synchronous speed is going to be 120 times your frequency, which is 60, divided by the number of poles. Well, if you had a 1-pole motor, well, you get the push, and then it's going to have to push it all the way around, and it's not really going to get a very good pull, and then to go to pull and push. So a one-pole motor, AC synchronous, isn't going to quite work like a bare minimum, a 2-pole motor here, where you would get a push and a pull, and as it came around, it would stop pulling, and it would push it, and then pull it, and pull it, and push it. So a 2-pole motor using this, just to your synchronous speed, 2-pole is going to be 3,600 RPM. There'll be slip in there. It's not going to be totally 3,600. You learned about electric motors, how you have the leading, lagging magnetic fields and all that kind of stuff in there. So, but theoretically, synchronous 3,600 RPMs, right? 4-pole runs at 1,800, 6-pole runs at 1,200, 8-pole runs at 900. And so the reason I did these is because when we talk about stepper motors, we're going to think about, I guess, having more poles or more steps in here to just kind of start to introduce, how this breaks down. Now, when we did that, and I'm not going to spend a lot of time on this, we just used hardwired start-stop memory circuit using normally closed overload to control the circuit and opening the circuit. So yeah, I'm going to lower this a little bit. I cut off my P. You've got your power circuit, your transformer, and then you got a control circuit down here at 120. And as we talked about, another thing is, we did a lot of 120 volt control circuits in 131, but a lot of these control circuits now are 24 VDC, just because it's a little safer, 24 VDC, and it will do the same thing. But there certainly could be AC or DC control circuits, all right? And then your 3-phase, we work with 208, but there's different things. Then we talked about forward and reversing, plug on plug-in, and it's you just got to have the correct starter. It's a bit more expensive, bigger in size, separate connections. And the big thing here is the forward and reverse, where you just switch the leads. Any of the 2 leads get swapped. You got to have some mechanical interlocks, or some electrical and or some electrical interlocks. You got to have some interlocks here, because you don't want the forward and the reverse on at the same time. So it's just this wiring here. That's what we did for the forward and reverse. We can hardwire and use ladder logic. We talked about, that's all hardwired. Soft and hybrid starters are an alternate form of a hardwired control circuit. We didn't do much of these. We did talk about these, because these soft and hybrid starters can accomplish reduced voltage starting. You did that in 232. You did reduced voltage starting, with a forward and reversing starter, or with a normal starter. And they have a memory function integrated into the hardwire, so this can have the holding contact put in there. If you're going to reverse this with a soft or hybrid starter, it still would require a separate reversing contactor. There's issues related to reduced starting torque and no speed regulation. Still, this is all on or all off, and your starting torque you got issues with that. And the way that this works, once again, we talked about soft and hybrid starters, is you have some solid state bridge here that is going to control the voltage for your soft start. 232, you did, I think, 3 different ways with resistors and voltage dividers. I don't know. You did multiple different ways to do low voltage starting. Well, the soft starter will do that for you. We talked about the hybrid starter, where you could have the solid state close the contactor, and or solid state close the power to the motor, and then once it was running, you could close the contactor. and then there wouldn't be any arc because the motor was already running. And then once the physical contacts have closed, you can turn off the solid state contacts, and then the motor will run. That way you will get rid of arcing. So we went through, kind of how soft and hybrid starters could be utilized, or in basically, how they worked. So then we moved on, to PLC motor control, and we've been doing that for, a year now. Start, stop, memory accomplished with a fictional bed, auxiliary and overload contacts. You monitor the state of the motor starter. You still need a forward and reversing starter to accomplish a change in direction. So it is cool to use the PLC to do all this, but you need forward reversing starter. For AC. Now, if you're doing DC, bidirectional DC, if you want to change the direction of a DC motor, it's shown here. You just change plus to minus to plus, and it goes in the opposite direction. And the way that you do this you could use an H bridge here to open and close these to get the path to flow from plus to minus, or to flow from left to right here, or go from right to left here, in some type of an H bridge here. I'm showing this here just because we're talking about using some type of a little bit of a bridge like this with our pulse width modulation a little bit later. But bidirectional, you can use some type of an H bridge to get this change the direction of a DC motor. We learned that a safety relay can be wired to the PLC programmable motor control. It can be a safety relay can be incorporated in a hardwired. It says hardwired or PLC programmed AC or DC. Add the safety relay, and remember the safety relay directly brings down the voltage to the machine controller, and so it's hardwired. It is bringing down the motor. All right, and then we can states can be monitored by the PLC. So the PLC wants to know that the safety relay has been tripped or hasn't been tripped, but it's not the PLC directly that's turning off the motor. It's the safety relay, hardwired, bringing it down. Speed control. So we learned that DC motor speed is varied by changing the voltage, and you increase the voltage, it goes faster. Less, it goes slower. You could hook a DC motor to some type of analog output, on a PLC, I guess, and then increase or decrease, and you get change in speed. Remember, on a PLC, it's not good for a lot of amperage, so you're not going to be able to turn something on. You need another device, almost like an interposing relay. If you really wanted to do it that way, it'd be some type of DC motor controller, if you could imagine that. AC motor speed is varied by changing the frequency, and we did that with our variable frequency drives. And there are a lot of things to consider, as we talked about, when changing the speed of a motor: constant variable torque, ampacity, heat generation, efficiency, low voltage start. All of these things they have to keep in mind when you're reversing, changing the speed of a motor, or acceleration or deceleration. All these things you need to keep in mind depending on what you want to do. Now, a really cool way to take care of a lot of this is the variable frequency drive. It can accomplish all those tasks mentioned so far for AC motors. You have to get a DC motor drive if you want to do something with a DC motor. But the VFD is what we did with the PowerFlex 525s. I can make a note of that here. That was the PowerFlex 525s, if you remember. And what that did is it used pulse width modulation to vary the frequency speed of the motor. And it's three-phase. Primarily you're talking about VFD, you're thinking a three-phase motor, okay? And you can do your reversing, acceleration, decel. It does soft starting, constant torque. The VFD, does all that. It's also got DCS, dual channel safety relays built in to a function of the VFD. And that's what's shown here. You got AC, you got a bridge here. So you take the voltage and you flatten it. Got a cap here, flatten it even more, and then you got this similar to what we did here. This was an H bridge. Similar here, you're gonna turn these switches on and off at a certain speed to allow electricity to pass into this motor. You close the switches longer, or close the switch is shorter to pulse the voltage to the motor, and it will run faster or slower. Okay, and you want to reverse it. It's very similar to the H bridge. You just the way that you're going to control these switches, and this is all internal to the VFD, and that's how that works. So we did that. Now, the VFD does not give feedback to from the motor, and it's typically considered an open loop. So you just want an open loop control of a motor. VFD is a good way to go. It gives you all that functionality that we talked about, and it works. Now, if you have really big motors, you can still get a VFD. It's just a really big VFD. That's these things get to be pretty expensive, and depending on what you're wanting to do, you start thinking like, well, I just need a forward reversing motor starter, or do I need a VFD? Well, yeah, it just depends what you need, for the cost and functionality and all this kind of stuff. VFD requires a little more training sometimes to program and set up. Possibly, you still have to know what you're doing if you're hooking up a reduced voltage motor starting circuit, all hardwired. So, yeah, just take a look at it. But I'm gonna tell you right now, a lot of this is done these days with a VFD instead of just wiring everything up. Depends on your application. And a VFD. A mathematical model estimates the speed and the distance or the number of rotations that the motor has done. We're using a mathematical model to do this. And then you remember on the capstone, we rolled that conveyor down and we put blocks at certain locations, wood block, metal block, stuff like that. Excuse me, I had a drink of water. But really, that's not fully exact because the VFD cannot compensate for changes in the load, and it's not fully reliably accurate to know the speed and distance that it's traveled. It worked, you can roll that worked fine. You could have rolled that part down the conveyor to some type of a hard stop or maybe a cylinder stop, and then shut it off, and you could get that part almost where you need it every time. Just depends on the accuracy, but ultimately, if you get some changes in the load or something going on in there, it's not, there's no feedback. Okay, so the first motor that we're going to talk about is a stepper motor, and this is a type of motor that will give you a more exact position and give you more exact speed control than compared to just turning on a motor and turning off a motor. And what this is, it uses a stepper motor controller to energize the coil of the stator, creating an electromagnetic field that repels. Listen to this: repels the rotor, causing it to rotate. You're like, hey man, this sounds like an electric motor. Yeah, it is. Yeah, right. That's what we're talking about. We're using magnetism, right? But what it does is it sends a pulse to the motor driver, which sends current to the coils in a specific sequence, and then it will start turning in the desired direction. You say, well, wait a minute, this sounds like an electric motor. Yeah, it is. Okay. It's a little bit different. It looks the same here. I got a little one here. It's got a rotor, and it's got a stator here, and it's got bearings on the end. So yeah, it definitely, the construction definitely looks like a motor. But what it is, it's a series of coils. And once again, we just talked earlier about 2-pole, 4-pole, 6-pole, 8-pole. And when I start looking at my cutaway here, you're going to notice the number of magnetic poles on the rotor. That's all these little bumps right here, all these magnetic poles. And so these are going to be your steps, so that when you energize, the coil, it is just going to click one step, okay? And it would stop. If you just pulse the voltage once, it would just click once and stop. It's not like all on or all off like an AC motor. And then what you would do is you'd click it and it would move another step, and then another step, and then another step. So you know how many steps this actually rotated. So if you had 100 magnetic poles on the rotor and you get 100 full steps, well, you got 360 degrees divided by 100, you get 3.6 degrees every time you step it. So now you're talking about, hey, I need to have this motor turn one full revolution. Well, then if you have 100 magnetic poles, then you know that you can hit it 100 times and it's going to stop. You go click, 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 and after 100, it'll be one full rotation. Micro stepping utilizes half step, so that's typically what you're going to see a lot is 200 pulses, which is going to be 1.8 degrees per step. So same thing, if you want to go 180 degrees, well then you hit it with half 100 pulses. 100 divided by 200 is going to be half a turn. 100 and 1.8 degrees per step. 100 times 1.8 is 180 degrees, and so you can step this multiple rotations. You want twice as many rotations, 400 pulses, right? A lot of times you'll see some variation depending on how complicated the motor is. Very simple ones like 6 poles would require 24 pulses. You might see that kind of a motor, but we'll be talking about a lot of times 200, 1.8 degrees per stepper motor here. So when you're going to do the stepper motor operation, you need an external controller that sends a digital signal to the motor driver, which translates the signal to pulse. And so we're gonna do this just for fun with a relay card to go over the sequencing of it. But that's what the controller does. The controller is gonna energize these coils in a specific sequence and creates your little electromagnetics to click, 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 click through it. The controller normally would do it because you have a lot to manage. The controller would know the rotation, the number of steps, the step angle is talking about here. 1.8 degrees per step angle is common. The controller is able to do that. And then there's also a lot of other considerations related to ampacity, the speed of the steps, that the stepper controller it can do this a lot smoother than the way that we're going to do it with a relay card. But we're just going to do a relay card just for fun to get the step operation down. But normally you would need the stepper motor controller. So you got full step drive, and here it's just showing coil 1 and coil 2. This would be a 4-wire stepper motor. That's what we're going to be using as a 4-wire stepper. It energizes the 2 coils of the 2-phase motor in a pulse direction command, and it causes the motor to move through a basic step angle. So you pulse it, and it's going to move 1.8 degrees, and then you would pulse the next one and move 1.8 degrees, 1.8 degrees, 1.8 degrees. So you can know how far you can move it through. And we're going to mess around, like I said, just getting one to run. You got the half step. Then this goes through and explains kind of how this works. That with the half step, it gets a little more complicated compared to the full step. The half step method has the advantage of doubling the precision and providing less vibration at low speed operation. So the half step, you get this interesting sequence of B prime, and then you got to do 2 at the same time, B prime and A prime A. So you're getting the instead of just going plus and then minus and then plus and then minus, or going plus plus and then minus minus plus minus minus plus plus, like that. This half step, you'll be energizing 2 of these at the same time to get your half step, and then you go A minus A, then you'll back to energizing 1 coil, then you're energizing both coils, then you're just energizing the BB coil for your set, and then reset, step, reset, step, reset, step. So the half step drive does give you a little bit more, but we're just going to program it just like a full step, just for fun. You want to get into the half step here? Yeah, go for it. Get a little more precision. So the stepper features, you got precision control. It moves in fixed steps, 1.8 degrees per step. It can achieve a high precision positioning and speed control, because you can hit those steps really fast, or you can slow those steps down. And you don't need any feedback to know that it's doing. It's got a high holding torque when the motor is energized. It is a strong detent holding in place. And so if you want to set it to a position, it's going to stay there, because you're going to have that permanent magnet in that coil energized, and it's going to hold at that step. open loop system. They can operate without a closed loop feedback system, which is more expensive. More, feedback is more expensive, takes more control because their position is known by the steps. But that's also, that's a benefit, the open loop, but it's also a drawback of the closed loop, right? The efficiency and power, they consume power even when stationary to maintain the holding torque. So that's what I was talking about. When you're at that step and it's holding it, you can't move it, that's great, but it's going to lead to overall efficiency, and it's going to get hot due to that continuous current draw. So the performance limitations or torque drop, it's going to decrease significantly as speed increases. And we talked about using a VFD to generate constant torque and stuff for an AC motor. That's good stuff to be able to do. But if you need high speed, high torque, you're going to have some limitations there. Limited speed range, their top speed is generally lower compared to other motors. You really got to click those steps off and on pretty quickly. Lower power density, low torque to inertia ratio. So stepper motors, they're okay. A couple other things. Step loss. Without the feedback system, the motor can lose a step. If you get too high of a load and for some reason it misses a step, or the acceleration is too fast, you're going to get position error and you wouldn't know it. All right, so that becomes the problem with the stepper motor. And they can be prone to resonance at certain speed causing vibrations. And although the stepper motor control circuits are often simple, they become complex when trying to mitigate those issues like resonance and the micro-stepping. I was just showing you the micro-stepping, where you're going step, reset, both coils, step, reset, both coils, step, step, step. And that becomes a little more complex. You need it's going to limit your speed of how fast you can get all that going. So yeah, there's some issues on the stepper lab here. It would typically require a PLC interface. You can get a stepper motor card that would go into your control logics, but then you would also need a stepper motor controller, because the stepper motor controller is designed to manage all that current, all that voltage, the speed of the steps. It'll be configured to match the motor, but we're not necessarily going to do that. And one reason we're not going to do that is because I don't want to invest a lot into stepper motors. You're not going to see stepper motors like you used to, because servo motors have really taken over. I just want to I want to give you a little bit of stepper motor background, because you run against one and you're trying to figure out how to troubleshoot it and stuff like that. But you're not seeing as many stepper motors out there, as you used to. That motor control handles the high current, high speed of steps, interlock of step voltage, all those kind of things. And we're going to simulate this with a relay output card, just for fun. Isolated VLC, we're going to use an isolated SLC 500 card, a 1746OX8, just so we don't short the 5-volt DC voltage. The stepper motors have got our 5 volts DC, and so hopefully we won't short anything out or burn any contacts, because it's not super high current. But let's just be careful not to do that anyways. And then in this lab, I've also got a potentiometer, or a linear potentiometer, a voltage divider, that we can incorporate when we take this stepper lab to make linear movement, to then verify that the stepper motor is producing linear distance or linear velocity that matches what we want. So we'll be adding an analog sensor, a linear analog sensor, to this stepper motor to be sure that it's acting. Now then you're getting a little more feedback on the stepper, and it's starting to act a little bit more like a servo. Okay, and we'll break into that, because it's a linear sensor, not a rotary sensor. But the big one that we're building into is the servo motor, and this allows for precise control of angular, position, velocity, and acceleration mechanical system. And the big deal is, you go, oh, here's a motor. Oh, it's got a bearing. Oh, okay. We've had motors with bearings. Oh, it's got a rotor. Oh, it's got a stator. So it looks just like another electric motor, and it is. The big thing is that it's got the encoder on the end. So the encoder is going to measure how fast and how many times this shaft is spinning, and that's the big difference on the servo motor, okay? Because the servo motor is closed loop. I talked a little bit just a minute ago about putting an analog linear sensor onto a servo motor. Yeah, we're kind of turning that into a little bit of a closed loop system, but this servo motor is fully integrated together into a closed loop, okay? It uses positional feedback. It could use a linear or a rotational position, or both, okay? But typically we're talking about a rotational position sensor. Throw the linear on there and be sure the two work together. Then you've got some really high precision. Control its motion. The input to its control is signal either analog or digital, representing the desired position of the output shaft. It's paired with some type of position coder, and that gives feedback, and it can be relatively sophisticated of how it's working, and that's why you want a servo motor controller to compare the measured position to the desired position to generate your error signal. You fed back into it, and then it adjusts for it. So, any one of these systems that we talked about, there's going to be error within that PID, and that you have to manage that error to get the output that you want. Well, the servo motor controller is good at running it, getting the feedback, and then processing it, and then remodifying your output to get that. Servo motor components. The servo motor will include a controller, servo drive, servo motor, and a power transmission mechanism. So we got a controller. Yeah, we got a servo motor controller, and a servo drive. So we're going to take our PLC and we're going to push stuff into the servo drive. The servo drive is really where all the current voltage switching is occurring in here per the instructions from the PLC. It is then going to move that information into the servo motor, and the servo motor will spin. This is going to control the spinning of the motor. The motor's got encoders on it, so it's going to be talking back and forth to the servo drive to be sure that it is doing what the PLC told it to do. And now the beauty of this is there's feedback all the way through here. So, this servo motor is an output, but it's producing analog signals used by the servo drive that can be monitored by the PLC if you want. And the PLC could then, if you want to do a PID or something, the PLC could then change the target value of the servo drive, I guess, which would then change the performance of the servo motor, which the servo motor is then going to tell it, how it's doing, and you could feed it back to the controller and modify these things. Like I said, you throw in a linear actuator here to be sure everything is working, and you could get a really cool control circuit that, in this case, this table's moving back and forth, that could be moving back and forth at a certain speed and for a certain distance, and you could be very accurate, okay? But another example of this is like a robot arm. That's got the robot controller is a big servo drive controller, and the robot arms each have a motor on them, and there's no there's no extra sensor to be sure that the robot arm went to where you said it would. But on the back of the servo motor, there's a sensor that says, hey, the arm is, I've turned this many times, the arm should be here, and it pretty much is going to be where you want it to be. You could add another analog sensor to a robot to be sure it gets where you want. And so the servo motor controller, it just looks pretty similar to what a lot of our stuff does here. You got a pulse width modulation going on inside of here. Here's your power MOSFET. Looks like we already just went over this a few minutes ago, and we went over it in the last class and the class prior to that. So it's looking very similar to what we've been working with. The main thing is that we just got an AC motor, and we've got a sensor on the end of it to say start speed up, slow down, spin this many times. And it's going to keep track of that. Okay, so that's what our servo motor controller is doing. So there's different types of servo motors. At the simplest of brush permanent magnet DC motors are used, and they work fine. That's what we got, permanent magnet DC motor. When you grab our DC motor and you spin it, it doesn't spin freely. You can tell that there's permanent magnets in there, and it almost feels like you're turning, I guess what you would think a stepper motor would feel like, click 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 click. But it's not. It's just that there's the magnets in there. Per the construction that we talked about a little bit earlier. They're small industrial servo motors are electrically communicate brushless motors, yes. Large industrial servo motors, AC induction motors could be used, yep. As long as you have the encoders on the back, you're good. Often with variable frequency drives to allow control for their speed, so you can, depending on what you want to do, how you want to set this up with a VFD or with a servo motor controller, with external analog sensor feedback. There's a lot you can do. Brushless, for performance and compact brushless AC motors with permanent magnet fields are used, affecting large versions of the brushless DC motor. So that's what we're going to have going right here, AC permanent magnet. All right, types of encoders. Simple servo motors may use resistive potentiometers as their position encoder, and this would be a rotary encoder. What I'm going to give you for the other one is a linear encoder, which is a voltage divider, resistive potentiometer, treated as a voltage divider. And they're used at the simplest, cheapest level because it's pretty cheap. I bought those linear ones that you're going to use for not very much. But there's issue with them. They wear out of their accuracy. It may be possible to electrically differentiate their position signal between speed signal, PID controllers that make use of that speed signal, and we're going to do a little PID control. Generally, we want a more precise controller. Well, what's that? It's the rotary encoder. Servo motors use the rotary encoder, and it would be absolute or incremental. A lot of times today, what you're going to see is absolute encoders, and they just determine their position when you power on. And they're more complicated, more expensive, versus incremental encoders will need to be homed. And what we're going to do when we do ours is, first thing we get ours running is we will home it so that it then has a zero position to start counting, I guess, how many times you've rotated from that home position. So we'll zero out that homing, that number, and then move from there. So I hope that makes sense. I've got a couple pictures later on here. So an optical encoder, which would not be an absolute encoder, it wouldn't require homing, but you can imagine maybe how it would work. You would have a light source and then a collector, emitter and collector, and then you've got this little disc here that spins, and there's little slots in here. And these little slots allow the light to pass through down here. So when this spins and the light passes through it, it'll count. And if it keeps spinning, it'll count 2 and count 3 and count 4 and count 5. And so you'll use these optical encoders to count, how many times it spins. You can use, like we talked about, resolver. If you want, to use resistance to do this, you can as well. So, but somehow on the end here, you are counting the number of steps, and this is where I'm trying to tie everything into thinking about maybe back to that separate motor, that it's almost like you're counting the steps, that 1, 2, 3, except whether you're counting 200 steps or something like that. But it's not a stepper motor. A stepper motor will just do the 200 steps. It actually won't count them, whereas this will count the steps, I guess. The servo motor is paired to some mechanical drive system, and it's going to give you a given task. Examples are robot linkages, conveyors, chain drives, screw drives, etc. We're going to pair ours to a screw drive, and it will need to be configured so that rotary motion is translated into linear motion. That means screw drives are different. The number of turns that you do per inch, how do you home it, your servo motor selection. There's things that you're going to have to go in set up, so that your mechanical system, because the mechanical system is just a mechanical system, the PLC or the servo motor controller doesn't know anything about it. There's no monitoring on it. unless you put that linear sensor on there, then there would be monitoring. But we have to set this mechanical system up so that when the PLC tells your system to do something, it's doing what you want, because you don't know that it's actually doing anything, or the PLC doesn't know that it's actually doing anything. There's no monitoring. It says instead of servo motor, sometimes a motor with a separate external linear encoder is used. So you can use a combination of a rotary encoder and a linear encoder. And so what you have here, this is similar to what we're doing. We've got the motor here. It's going to have an encoder on the back. So this motor is going to be being told to spin a certain number of times at a certain number of speed. And the rotary encoder is going to be counting that to be sure that that's what's occurring. And then this spins, and there's a screw drive, and then this table is going to move back and forth. And this table is going to move back and forth depending on how we set it up. How many rotations does it take to move 1 inch or 2 inches, and all the details that you're going to need for this mechanical system, you're going to enter in there so that it will do all the math for us, right? But what you can also do here, this yellow, is you can put a linear encoder on here, and that can be an analog feedback back into the PLC. So if you say, hey, move this item 10 inches, and then this moves 10 inches, well, this linear encoder right here can be set up, it can be scaled, and then input an analog card and say, yep, I moved 10 inches, or I only moved 9.9 inches, okay? Or how about this? This motor can be saying, all right, speed up, then run really fast, and then start slowing down, and then stop. Well, this linear encoder can measure that and see, yep, oh, it's speeding up, wow, it's going really fast right now. Oh, it's starting to slow down. Oh, it stopped. This linear encoder can send all that information back to the PLC to be sure that this motor is doing exactly what it wants. And then, like I talked with the stepper motor, you can put in a feedback control loop here, maybe like a PID in here to govern this, to be sure that, hey, this thing is really working exactly like I want it to. Especially if you're getting some variable torque on here, that's, this motor is still gonna, because it's got the encoder, it's still gonna compensate for that variable torque, or at least try to, right? But you put a linear encoder on there, pushing it back to the PLC, well, then you can be sure that this system is you're getting your feedback, you're getting your monitoring. It is doing what it says that it's doing. So this is kind of the gist of what we're setting up. Although the linear encoder, we're going to put that on the stepper motor application just for fun. And so we'll see how we do. It says servo trainer board. So these will be, I might have you hook some of these up just to see. There's high voltage, and there's it'll take some inputs. It'll take a prox, for example. It's too bad the servo controller doesn't take the analog signal directly. The analog linear sensor would have to go back to the PLC. But maybe I'll have you set the servo trainer boards up a little bit. I'll get them mostly built for you. You can make some final connections depending on how we're doing. It says no quiz, but then we will have the lab here, and I don't know, the lab shouldn't be too much. I just want you to have a little bit of fun, see what it takes to run this, and note that the servo motor lab uses a state machine, and you'll see that it's going to be interesting. Like, hey, all right, I'm going to shut this thing down. Well, it makes its way all the way through the process before it shuts down. And you're like, oh, do I want that? Should I change something like that? But, there's a lot that we can do with this on the capstone if you want. You want to use the DCS safety on this, or if you want to put linear encoders on to check the motion, or, whatever. I just want to get you an introduction to this. And later on, if that's what you want to do and apply it, we will try and set that up. All right, that's what I got. No quiz. I will see you guys in lab.